Hi, in this video, I'll be going through what are normal groups and how they are related to quotient groups. And so, we first define what is known as the centralizer of a set A in the group G. And this is, you just find all the elements in G such that G inverse equals to A. So you can also think of this as GA equals to AG. So it's basically all the elements that commutes with all the elements in A. And that's known as the centralizer of A. And what we want to say now is that the centralizer of A is a subgroup of G. And you can easily show it over here. And I'll leave it to you since we have already done it many times to how do you prove that a set is a subgroup. And so some examples is that if G is an abelian, then of course every element commutes, so the centralizer is just the whole of G. And we define the center of G to be all the elements in G that commutes with all other elements in G. So this is called the center of G. And we can easily say that the center of G is just the centralizer of G, showing that the center of G is just a subgroup of G as well. Then we define what is known as a conjugate by G as the element G and G inverse. And so then we form the set of conjugates. The conjugate set is like G and G inverse. So then n just runs through all the number n's, capital N's. And the element G is said to normalize G and G inverse if it equals to n. And then we define this to be the property of normality. And we say that a subgroup is normal if every element in G normalizes n. Meaning G and G inverse equals to n for all G. Then we write this notation, a triangle. And what does G and G inverse equals to n means? It means that Gn equals to ng. But what we would like to note is that it is saying that elements in... It does not mean that Gn equals to ng, like little n, where n is element of n. But it means that Gn is an element of ng, meaning it can be written as the form n prime times g. And likewise for the other side of the inclusion. So this is what it means to be normal. It means that every element in G normalizes n. And then we can define the normalizer now to be all the elements in G that normalizes n, that normalizes the whole set A. So we define this to be the normalizer. And we can see that if A is normal, then all G's satisfy this property, meaning the normalizer of a normal group is just the whole group G. And we can further prove that the centerizer of G is actually a subgroup of the normalizer. And the steps are very similar to what you have always done. Now, if G is a billion, if we take this example that G is a billion, then of course the center is G, and the centralizer normalizer are all equals to G. And you can just prove it by showing this definition to be equals to G itself. And then we now prove, or we state this theorem 6, which says that if n is normal in G, then it is equivalent to any of these 5 statements. And really, the proofs are very simple and straightforward, and it's because 1 implies 2 is very direct. The normalizer of n equals to G. I've already explained why. And now we know that if the normalizer of G equals to G, it means that this criteria equals to G, but this criteria is just the criteria of GA equals to AG. And this means for all G, GN equals to NG. So you are done. So you've proven this direction to this. So 1 implies 2 and 2 implies 3. Now you want to take 3 implying 4. And really the operation of proposition 5 in Dummy and Fruit says that G and G inverse is an element of N for all G and for all N. But that is really just follows from this definition, so it's again the same. And if G and G inverse is an element of N, that means G and G inverse, this conjugate set, is a subset of N. And so now it remains to show the other inclusion so that it equals. But of course N is a subset of G and G inverse, because if this occurs for all G, then you can just take G to have like 1. And so you already... So how do you see that N is a subset of G and G inverse? Well, you just take an element in N, and then because it fulfills this condition, this element in N can be written in a form like this, which then is an element in... So it's like N prime equals to G and G prime. Then G inverse. Then now this N will just equals to G inverse N prime G. And this G inverse and G are elements in big G. And so now you can just write all the elements in N as an element in the conjugate set. So you're done. And so why do we want this normal property of a set? It's because now we can define what is known as the quotient group. And it's just the set of cosets of N in G. And when you define it with the binary operation as the following, we can actually check that it has an inverse identity and it is associative. And this operation is defined for any representative of the coset. So you can have G prime N equals to Gn, and H prime N equals to Hn. Then G prime Hn N equals to Ghn, and they are the same. So only when you have the normal property, then actually this binary operation is well defined. And you can actually take a look in the textbook for examples to show when this N is no longer a normal group. It's actually the binary operation may not be well defined. So we only can form quotient groups when N is normal. So that's one of the important things to take note. And an example of this is the set of integers, and we form the cyclic group, so it's just NZ. And this is of course a normal group because it's commutative. And the cosets will be K plus H, and it's just K plus H running through all capital H. So these are just the equivalence classes. So you form the set of this, it's just the set of equivalence classes. And these are the n distinct cosets, so it's 0, 1 all the way. And so then the quotient group will just look like the modulo group. And so they are actually the same thing. And later when we talk about isomorphisms, you can actually just say that they are isomorphic to one another. So, like earlier, we have stated that the operation can only be well defined if and only if G and G inverse is an element of N for all G and for all N. And this is really equivalent to saying N is normal in G. And so the proof follows over here, and it states that assume that the operation is well defined, and then you just take different representative of the cosets. You can then prove that G and G inverse is an element of n. Because we can just let u equals to 1, u1 equals to n, v and v1 equals to G inverse, and then we're using the assumption, we can deduce that the following occurs. So G inverse n equals to ng inverse n. And this really you can just multiply by G throughout in a sense, and it's just saying n equals to G and G inverse n. And so G and G inverse must be an element of n. And you're done. And now if you assume the converse, you're saying that G and G inverse is an element of n, and you want to prove that the operation is well defined. So you suppose that you have other representative of in the cosets. So you want to prove that u1 v1 is still an element of u vn. And it's really straightforward because u1 v1 can be written as un vm, and then now you know that un, you can take multiplying by v and v inverse. So u v inverse n vm equals to uv, then you multiply this conjugate times n. And this conjugate, now you know that it lies in n. So it's n1. So it's just uv times n1m. And n1m is closed under products. So n1m is still an element of n. So now this is just uvn. And so you're done. And I'll let you to check that it is indeed a group where it has the inverse and identity. So part 2 is just checking that, and I'll leave it to you to read it on your own. So what we want to move on now is what is known as group homomorphisms, and really, as the author puts it, the study of quotient groups is equivalent to studying how these homomorphisms of G work. And what is a homomorphism then? Well, a group homomorphism is from G to H such that it respects the operation. Meaning you take x star with y and then you phi it. It's actually just the same as phi of x diamond with the phi of y. So what you're saying is that it respects the group structure in both the domain and codomain. And the picture shows how we can apply it to quotient groups. Because you can think of H as a subgroup, and we now take all the fibers in G and we project down into H, meaning we are forming like, so each representative here in H, you can represent them by this cosets. So you want the cosets to be represented by a single element now. So all these have like similar properties as you call it. So you can quotient off by H. And what you want is now you just pick an element here and you project it down into it. And this is what we are trying to get, this homomorphism. And by studying this phi, we are able to understand the group structure of G quotient out with H. So this picture should show you how it works and what we are trying to do. And this example is really a good illustration of it. So we just take a cyclic group of order n and we define the homomorphism from integers to Zn as phi of a equals to x to the power of a. And then we show that this is a homomorphism because phi of a plus b is just the same as x to the power of a plus b. And that's the same as x to the power of a times x to the power of b. And x to the power of a is phi a, and x to the power of b is phi b. And then we can show that the pre-images is just the equivalence class of A mod n. So x naught is just 0 n, 2n, 3n all the way. And then x1 is 1, 1 plus n, 1 plus 2n all the way. So now you split your Z, you partition them into the set of cosets. And then your quotient group, which is the Zn, you can just quotient out with respect to n here. So by quotienting out with respect to n, you delete all this away basically, and then you can see that we are represented by the same element A. So then you project this element down, the representative, and do this quotient group. So you can see that the set of cosets now is looking like your quotient group, and actually it is your quotient group. So you can think of it as isomorphic to each other in a sense when phi is bijective. So then we define the kernel of this set to be the set sending to the identity element 1 here. And this is just the kernel of, we call it the kernel of the homomorphism. And this kernel, and now we want to prove theory propositions about group homomorphisms to better understand it. And it's saying that the identity is sent to the identity, and that should be clear. You can read the proof of 1, 2, and 3 in the textbook, as they're very straightforward. Now I will show that the kernel is a subgroup, and that's because the identity by number 1 lies in the kernel, so the kernel is non-empty. And you can prove that it respects group operation, and so G star with H inverse is still an element of the kernel, and so kernel is a subgroup. You can likewise show that the image is a subgroup under using the same way. And next we want to show that phi is injective if and only if the kernel is 1. And so if the kernel equals to 1, then you just take two elements in G and show that phi of x equals to phi of y. You want to just show that x equals to y. So then we just consider the phi of x y inverse, and this is just phi of x times the phi of y inverse, and phi of y inverse is just phi y inverse. So phi of x times, but phi of y equals to phi of x over here, so this is just phi x times phi x inverse, which has to be 1. And since you know the kernel is trivial, so x times y inverse equals to 1, which implies that x equals to y. Hence, phi is injective. And conversely, if phi is injective, then we already know that phi of 1 equals to 1, meaning that the kernel of phi must equals to only 1, since it's a unique element. And certain other properties, before we end the video, will be that two group homomorphisms, when you compose them, is still a group homomorphism. And this really means that you can actually show that the homomorphism group of from K to L, so the set of homomorphisms of automorphisms, I mean, so it must be bijectives from H with the group function compositions forms a group. And if phi is bijective, then of course phi, the inverse, is also a group homomorphism. And really that's because K and L be elements of K. You want to show that phi inverse is a group homomorphism, meaning you just take the phi inverse of K and L, and you can actually just say that because phi is bijective, so there's an element G that phi of G lands in K, and there's an element H such that phi of H equals to L. So you replace H and L respectively, and this can be grouped together, so it's just phi of GH, and this phi inverse and phi of H will cancel each other, so it's with GH, and G and H now you replace back, and it's just phi inverse K times phi inverse H. And so this really shows that the group of automorphisms is a group. So that's all for this video. I've come to the end of this video and I hope you have now a better picture of what the quotient group is using the ideas of group homomorphisms. And we study later on, we shall see the importance of quotient groups and group homomorphisms. So I'll catch you in the next one. Bye!